So we are going to see the different architectures available for transmitter so that it can be used for the current application scenarios. So we have one conclusion is certain from what we have studied. The PA frequency and the oscillator frequency uh, should not be same, because we have the issue of the noise and other oscillator pulling happening. So for confusion, we call the LO frequency, to avoid confusion, we call the LO frequency to be omega LO and the carrier frequency to be omega C. Carrier frequency is going to be the actual frequency at which the up conversion is going to happen. Okay, this task we can avoid oscillator pulling by choosing omega LO and omega C to be far away from each other, so that there is going to be no relation between them. Thereby, we can eliminate unnecessary effects in our receiver transmitter. So, and the most commonly used relation is we'll take omega LO to be 2 times omega C. So, if you have omega C followed by omega LO, LO, which is 2 times your omega C. So, a divide by circuit is going to used, which will convert your omega LO to divide by 2, and the frequency will be used for your carrier. So see here, so LO frequency is divided by 2 and it is given to the mixers. Output is added and power amplifier is being sent. So the architecture is very popular because injection pulling is reduced, because we have separated omega C and omega LO far away from each other, so that image pulling, injection pulling is greatly reduced. And the divider will directly provide a quadrature phase of the carrier. So we need not generate a quadrature phase, and the divide by 2 circuit will directly produce the quadrature phase, and it is going to be popular for these two reasons, but it is does not entirely eliminate injection pulling. So injection pulling is reduced, but it is not getting eliminated. So there might be a second harmonic carrier that might be still be pulled, even though the fundamental frequency pulling is reduced. That second carrier frequency of the carrier over 2 omega C, that might be pulled here still. So unless proper isolation techniques are followed and proper layout is done, we cannot suppress this effect. And the principal drawback will come from the speed required of the divider. So divider has to act in a faster manner, and it should provide the quadrature phase in the same quadrature signal in the same time to I and Q channel. Otherwise, you cannot reduce the oscillator pulling. And operating at twice the carrier frequency, the divider may become the speed bottleneck. So divide by 2 in analog domain, if you are going to do that, is going to be a cause of concern for you, because the divider has to be, this divider will decide the speed of your transceiver. So because of this divider, many architectures are going to perform very slow, and the divided design is going to be taking a substantial amount of time. So another approach is deriving frequencies through the use of mixing. So mixing the output of two oscillators operating at omega 1 and omega 2 can yield some difference. So now you can employ an oscillator, you can use the